So let's move on and conclude this segment by deriving the simplified cylindrical coordinate case. Let's look at a loop that's in the xy plane, resulting in a current density in the z direction. So our loop is going to be here, parallel to the xy plane. And let me just draw this in, and we would expect the current to be in what direction? So if we define this to be in this from positive z looking down towards negative z, if we define this as going counterclockwise, you would expect the current to be in the positive z direction. Let me draw this out in 2 dimensions, a little bit larger, and so that our derivation is a little bit easier to understand. We're going to look at the H field at this location, and specifically H is only going to have an x and a y component, just to keep things simple. So we have H naught x in the x direction plus H naught y in the y direction. And let's define that location as x naught, y naught. So this location here is x naught, y naught. And the loop, since we're talking about a small area, we can approximate it by doing a rectangular loop. That way we can use our Cartesian coordinate system to our advantage. Let's call this 1, 2, 3, 4. So we're going to go and do a line integral from 1 to 2 to 3 to 4, and then we're going to shrink it to a point. And the end goal is that we expect to arrive at the result that the resulting field is going to be in the z direction, is going to be equal to, let's just take a look here, is going to be equal to d by dx hy minus d by dy hx. All right, let's go. We're going to define this length here as delta x, this length here as delta y. And the one trick that we're going to use, the numerical approximation and numerical technique that we're going to use, is the fact that if we wanted to find the field at this location, let's say we want to start out by finding h from along 1 to 2. So the h that's defined at this location over here, we're going to start with, it's going to be the y component, right? Because it's going the y component. So we're going to start with hy at the location that we have information on, which is the location x naught, y naught. And then to extrapolate what the value is if we shift by 1/2 delta x, we're going to take the derivative with respect to x. So d by d, we're going to take this hy, we're going to take d by dx, which gives you the rate of change as you move in the x direction, and then we multiply it by the amount of change that we want to shift it by. In this case, if this whole side is delta x, we're going to shift it by 1/2 delta x, right? So this is, again, we have our value in the center here, and then to shift it over by 1/2 delta x, we multiply it by the slope, right? The slope is rise over run, so if you multiply it by run, you get the rise, which is the change in hy. So for along going from 1 to 2, the field in the y direction is going to be hy. It's going to be this expression over here. So for the first line segment, which is the one that we just did, h dot delta L for line segment 1 to 2 is going to be what we had here. So hy plus 1/2 d by dhy of dx delta x. So I'm just going to pull the 1/2 out. And then that's going to be in the y direction. And in this case, our dl is going to be delta y in the positive y direction. Now let's do the same thing for the remaining 4 sides. So h dot dl going from 2 to 3 is going to be, we're going to be using hx, and then we're going to shift it up by half a delta y, right? So that's going to be 1/2 d by dhx, and we're shifting it by y by half a delta y. Should be nothing there. And then in this case, this is in the x direction, and our dl is going to be in the negative x direction. So delta x, negative delta x in the x hat direction. Then going from 3 to 4, we're going to have hy, but now we're going to shift in the by negative 1/2 delta y, so minus 1/2 d by dhy of dx delta x. So we're going to shift by 1/2 of delta x, and it's going to be in the y direction, and in this case our dl is going to be negative delta y in the y hat direction, and our last side h dot delta l from 4 to 1 would be this here, so that would be hx, and we're going to shift it down by half a delta y, so minus 1/2 d by hx dy, which is a slope, times 1/2 delta x, 1/2 delta y, where I pulled the 1/2 out here, x hat, and then in this case our dl is delta x in the x hat direction. So now let's add all four of these together. If we add all these together, you'll see that the hy's cancel, because this hy and there's a negative sign here, so these two hy's cancel, and these two add together. So you're going to get therefore you're going to get d by hy over dx. Similarly, for the hx d by dy component, these two are going to combine but have a negative sign, right? There's a negative sign over here, so you have negative 1/2 and negative 1/2, so these combine to give you negative dhx by dy, and then the hx's cancel, right? You had a negative hx, in this case you have a positive hx, so the hx's go away. And don't forget that we also have delta x, delta y across all the terms, so you can factor out the delta x, delta y. And that, based on Ampere's circuit law, is going to be equal to I enclosed, which is going to be equal to the current density times the total area, right? J times delta x, delta y. In this case, J is in the z direction. And since we're taking out the z direction, we're not going to worry about the vector. And so now, let's shrink. Let's take the limit of delta x, delta y goes to 0. So what that means is that before, when we were doing our h dot dl, because we were approximating it as a rectangle, technically this should be approximately equal to this expression here. If we take the limit of delta x, delta y goes to 0, then it becomes a hard equal sign. So if we take that limit of the surface area goes to 0, just like in Gauss's law where we shrink it to a single point, you get h dot dl is going to be equal to d by dy, d by dx of hy minus d by dy of hx is going to be equal to the current density. And so if you do the same exercise in two other dimensions, you'll get the other expressions that form the final result for Cartesian coordinates. Which I'll show over here. So to summarize, we talked about Ampere's circuit law in differential form, and it's the same analogy of Gauss's law between integral form and differential form, where you shrink the concept down to a single point. Now in the case of Gauss's integral, law, Gauss's law in integral form, it was a surface integral of a closed surface. If you shrink it down to point form, you get the divergence. In our case, it's a line integral, a closed line integral. If you shrink it down to a point, you get the curl operator. We talked about how to do the curl operator algebraically. We also gave a little analogy, the wine bottle corkscrew analogy, where if you let the fields push the corkscrew around, the amount of swirl will apply force onto the cork of the wine bottle in a direction that's perpendicular to the direction of the spinning. And then we wrote out how it would look like in Cartesian form. I was lazy and just showed you how it would look like in the other two coordinate systems, cylindrical and spherical coordinate system. And then we also looked at the actual writing out and then shrinking process, just like we did for when we were developing the divergence. But in this case, to make it simpler to see, we just looked at a situation where our closed line integral was on the xy plane, resulting in a curl that was in the z direction. And as you can see, if you kind of do this rectangular line form, if you shrink it down, you end up with the expression, portions of the expression, or the z vector curl portion of the curl formula in Cartesian coordinates.